So our goal for this question is to find the arc length of y equals the square root of x on the interval from 0 to 4. Before I do this, I just want to warn you that the integrals for arc length tend to get very challenging. So let's just keep that in mind as we move forward. Just a quick reminder, remember the change in arc length squared should be the change in x squared plus the change in y squared with Pythagoras if we're dealing with a small curve like this, right? Change in x, change in y, and that's change in s. So change in s with Pythagoras is the square root of the change in x squared plus the change in y squared. And we divide both sides, or divide and multiply by change in x. So change in s is the square root of the change in x squared plus the change in y squared divided by the change in x times the change in x. And then if you divide by change in x, that's the same thing as dividing by the square root of change in x squared. We see that. And then we can multiply, or excuse me, make a single radical. So change in s is the square root of change in x squared over change in x squared plus change in y squared over change in x squared. Then what do we get? Then we get change in s. Square root. Change in x squared over change in x squared 1 plus change in y squared over change in x squared. Change in y over change in x squared. Change in x. And then, of course, we have to sum them all up. So the total arc length s is the sum of all those. Sum of the square root of 1 plus change in y over change in x squared, change in x. And then we finish this off by saying what? Shrink delta x to 0. And we get sum is the integral from a to b of the square root of 1 plus change in y over change in x becomes dy dx as the limit as delta x goes to 0 squared dx. And that's the formula we're working with. That's where it comes from geometrically. That's what we're trying to use. So again, what's our question? Arc length of y equals root x on the interval from 0 to 4. And that's the formula we get from studying the geometry. So let's do it. Starting with y equals the square root of x, which of course means y equals x to the 1/2 power. So what is dy dx? What is the derivative of y with respect to x? It is 1/2 x to the negative 1/2. What is dy dx? 1 over 2 times x to the negative 1/2, or 1 of 2 root x. Our formula requires dy dx squared. So what is dy dx squared? It's 1 over 2 root x squared. What do we get? Dy dx squared is 1 over 2 squared is 4 root x times root x is just x. What was our formula that we motivated on the previous page? S, the arc length, is the integral from a to b of the square root of 1 plus dy dx squared 1 over 4x dx. And that doesn't look bad, but guess what? It is. That gets very challenging for us to work with. So what is that going to be? How are we going to make sense of that? What tool are we going to use to make sense of that? Well, let's simplify the algebra first to see where this is going. So getting a common denominator, s is the integral from a to b, square root of 4x over 4x plus 1 over 4x. S is the integral from a to b of the square root of 4x plus 1 over the square root of 4x. So S is the integral from a to b of the square root of 4x plus 1. Square root of 4 is 2 root x. And you look at this and you ask yourself, what strategy will work? What strategy will work? And our arc length was ranging as x went from 0 to 4, if you recall on our first page, right? Y equals root x and the integral from 0 to 4, interval from 0 to 4. Let's put those endpoints in as well. S is the integral from, as x goes from 0 to 4. Keep in mind that those are x values of root 4x plus 1 over 2 root x. This is a nasty integral. So think about that. How to evaluate such an integral. What's our tool that we're going to use? So we have a bunch of techniques you can try. I like trig substitution on this. So think about how you would build your triangles to work in this context. What would that be? Well, root 4x plus 1 is a sum. So root 4x plus 1 has got to go on the hypotenuse side. And you'll notice that 2 root x is going to go on another side. A squared plus b squared. So I'm going to put 2 root x here. We'll call this a or b, whatever you want to call it. And I'll call it b, I guess. And we're going to say a squared plus b squared equals c squared as we try to make sense of this triangle. A squared plus b squared is c squared. 2 root x squared plus b squared equals root 4x plus 1 squared. So 2 squared is 4, root x squared is x, plus b squared equals what? Equals 4x plus 1. So the 4x's go away. B squared is 1, so b is 1. So here is our triangle. We have successfully built the triangle using Pythagoras. So let's circle that triangle. I need theta in there, of course, to do my trig substitution. So I'll put theta here. There is theta. And now we've got to go ahead and do some trigonometry with that. What is the simplest part of that? How can we make sense of it? I need a 2 root x, I need a root 4x plus 1, and I need a dx. Those are all things I need to get to be able to finish this problem. So what am I going to start with? How about opposite over adjacent? That's what? That's tangent. So we'll say tangent of theta is 2 root x over 1. Might it be helpful to square both sides, maybe? Maybe we can square both sides. If I square the left side, I get tan squared theta. If I square the right side, 2 squared is 4. Root x times root x is x. So I have tan squared theta is 4x. Now we're going to take the derivative with respect to x of both sides. Derivative with respect to x of tan squared theta equals the derivative with respect to x of 4x. Derivative of something squared is 2 times the something times the derivative of the something. So the derivative of tangent squared would be 2 times tangent theta times the derivative of tangent theta. The derivative of 4x is just 4, of course. So where does that put us now? We have 2 tan theta. The derivative of tan theta is secant squared theta, d theta dx equals 4. We need to solve for dx. So divide both sides by 4, multiply both sides by dx, and what does that give me? So 2 over 4, 1/2, tan theta, secant squared theta d theta. Equals dx. So I have my substitution for dx. Here's dx here that was done with the trig substitution. There's dx up there. Notice I also have a substitution for 2 root x. Do we see that? We have 2 root x equals tangent theta. That was given to us earlier, right? 2 root x equals tangent theta. So we'll circle that. We have that substitution. So the only thing that we need to finish this is to figure out something for root 4x plus 1. And I hope that's obvious. If we use cosine, cosine is adjacent over hypotenuse, or secant is hypotenuse over adjacent. So looking at that last piece of this puzzle, where does that put me? Cosine theta is 1 over root 4x plus 1. So take the reciprocal of both sides. Reciprocal of cosine is secant theta. Reciprocal of root 4x, 1 over root 4x plus 1 is root 4x plus 1. So where does that put me? That is the third piece. Good. So we're going to worry about the endpoints at the end of the problem. I'm not going to worry about it right now. So 0 to 4 will be there eventually, but this root 4x plus 1 will become secant theta. Dx will become 1/2 tan theta secant squared theta d theta, and 2 root x will become tan theta. We'll make all those substitutions and we'll see what we are left with. So this was our most recent position. Secant theta, S equals integral from 0 to 4 of root 4x plus 1 over 2 root x dx, which will become what? Worry about the endpoints later. Root 4x plus 1 was secant theta. 2 root x was tan theta. Dx was 1/2 tan theta. That divides out. That's nice. Secant squared theta d theta. So what do we get then? S will be 1/2, because the 1/2 comes out in front. The tan thetas divide out. And we are now left with one of our favorite integrals. It shows up often, the integral of secant cubed theta d theta. And then we'll worry about our endpoints here shortly, and then we'll see what we get. All right, our endpoints. X goes from 0 to 4. Emphasize the fact that those are x values that go from 0 to 4. And then these are thetas that we're dealing with here. Let's go to a piece of scratch paper, quickly do the integral of secant cubed theta. So how do we do that? Integral of secant cubed theta. Again, we are just trying to find the arc length of a parabola. And to find the arc length of a parabola, I am required to do the integral of secant cubed. So that's pretty rough. That's pretty rough. What we're going to say here is this is the integral of secant times secant squared. Integral of sec theta times secant squared theta, d theta, of course. And this requires integration by parts. So u is sec theta, dv is secant squared theta, d theta. So du d theta, the derivative of secant is secant tangent. Du d theta is sec theta tan theta. So du is sec theta tan theta d theta. Integral of dv is integral of secant squared theta. d theta. So integral of secant squared, of course, is just tangent. So v is tan theta. So where are we at now? We have integral of secant cube theta. uv, uv, uv. Secant tan theta, sec theta tan theta. Minus the integral of v du, which is sec theta tan theta, or sec theta tan squared theta. And at this point, you might be extremely frustrated with just how tedious this is, but there's another magic trick we need to use to finish this problem, namely the identity. 1 plus tan squared theta is sec squared theta. So tan squared theta is sec squared theta minus 1. So now I have the integral of secant cube theta equals sec theta tan theta minus the integral of sec theta times secant squared theta minus 1 d theta. And we keep on working. Integral of secant cube theta equals sec theta tan theta minus sec cubed minus sec theta d theta. What do we have? Integral sec cubed theta equals d theta. Should be a d theta there, of course. Missing a lot of d thetas. D theta, d theta, d theta. Integral of secant cube theta d theta equals sec theta tan theta minus the integral of secant cube theta minus plus the integral, there should be a d theta there, of course, minus plus the integral of sec theta d theta. Now, what's the mathemagic trick? Add secant cube theta to both sides. Plus integral secant cube theta plus integral secant cube theta d theta. And where does that lead us? Sec cube theta plus sec cube theta is twice the integral of sec cube theta d theta equals sec theta tan theta. That subtracts out plus the integral of secant theta. Okay, well, the integral of secant theta is log secant plus tangent. Maybe you have that memorized, or you can do that with a u substitution. Twice the integral of secant cube theta d theta is sec theta tan theta plus 1/2 log absolute value sec theta plus tan theta. Now, I really should write plus c here, but I'm not going to do that because we're going to substitute in our endpoints eventually. Divide everything by 2. Oops, I was a little quick on the draw there. Sec theta tan theta plus log sec theta plus tan theta. Now divide everything by 2. Integral of sec cubed theta d theta. Divide this first piece by 2, 1/2 sec theta tan theta plus 1/2 log sec theta plus tan theta. Okay, well, we need to go back and look at our triangle. What was our triangle? It was this page. So looking at this page, do we say what secant is? Well, cosine is 1 over root 4x plus 1. So secant theta is root 4x plus 1. Looking at our triangle. Hypotenuse over adjacent, root 4x plus 1. What is tangent theta? Tangent theta is opposite over adjacent. Tangent theta is 2 root x. So we'll keep all that stuff in mind. But we need to recognize something, that all the way back here, this is where we were. We had originally had S was the integral as x goes from 0 to 4 of root 4x plus 1 over 2 root x dx. And then we got down to this point where S was 1/2 times the integral of secant cubed theta. So now we could actually plug that in if we want and say S is 1/2. Again, we know x is going to go from 0 to 4, so we're going to have x's. Secant cubed theta, I'll just quickly write this version down. 1/2 sec theta tan theta plus 1/2 log sec theta plus tan theta. Integral's done. Integral sign's not there anymore. As x ranges from something to something. But we're multiplying in this 1/2. Multiplying in that 1/2, what's that going to give me? S is 1/4 sec theta tan theta plus 1/4 log sec theta plus tan theta. Evaluated as x goes from 0 to 4, but again, I need the x's. So what did we say previously on the previous page? Secant theta is root 4x plus 1, tangent theta is 2 root x. Make those substitutions. S equals 1/4. Secant theta is what? Root 4x plus 1. Tangent theta is what? 2 root x. Plus 1/4 log. Secant theta root 4x plus 1. Plus tangent theta is 2 root x. Evaluated as x goes from 0 to 4. Okay, there we are. Are we ready to finish this? I hope so. Let us take a look and see what we get. Plugging in the 4 first, plugging in 4 for x. S is 1/4 root. 4 times 4 is 16, plus 1 is 17, times 2 root x, plugging in 4, 2 root 4, plus 1/4 log absolute, plugging in 4, what do we get? 4 times 4 is 16, plus 1 is 17, root 17, plus 2 root 4. That's the first part, minus plugging in 0. Plugging in 0, what do we have here? 1/4, 0 plus 1 is 1, but 2 root 0 is just 0, so that piece is 0. Plus 1/4, 2 times 0 is 0, 4 times 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, but natural log of 1 is also 0. So we'll be thankful for that all of that went away. So where does that leave us? S is 1/4 times root 17. Root 4 is 2, 2 times 2 is 4, plus 1/4 log. I don't think I need absolute value because everything is positive. Root 17 plus root 4 is 2, 2 times 2 is 4. The 4's cancel or divide out. What are we going to finish with? S is root 17 plus 1/4 times the log of root 17 plus 4. Can we get a decimal approximation of that? Let's see what that's going to be. square root of 17 first. Square root of 17 plus 1/4 times the natural log of root 17 plus 4. And I get an answer about 4.647. Now, I want to ask you if you think that seems reasonable. Does that seem reasonable to us? Well, one of the ways I could answer that is to visualize the graph that we're working with here. So here's the graph of y equals the square root of x as x goes from 0 to 4. Now, if I would draw a straight line, here I'm going to draw the straight line in blue. We see what that is from 0, 0 to 4, 2. That's up 2 over 4. Using Pythagoras, 16 plus 4, 20. This is the square root of 20 approximately. What is the square root of 20? It's 4.47. So you see the thing in red has got to be bigger than that, right? The shortest distance is a straight line. So it's got to be bigger than 4.47. Is my answer a 4.647 a little bit bigger? It is. And there's one other way that I'm going to check this. Let's go all the way back to the integral here. I want to run to a computer algebra system. I will use Wolfram Alpha to see if this gives me the same answer. So I want to jump to Wolfram Alpha and I want to run that integral and I want to see what I get. So let's do that. If I can. So I want to integrate what? Integrate. We're going to take a look at upstairs is square root of 4x plus 1 divided by downstairs 2 times square root of x. I don't like capitals. Times square root of x dx as x ranges from 0 to 4. And again, we had our decimal approximation. Let's see, a 4.647. Let's see how close this is. What's it going to give me? Gives me 4.647. Notice we have an exact answer. Wolfram Alpha was actually unable to do the symbolic integral that we were able to do. So this is an example of us being a little bit smarter than the computer. All right, very, very tough problem. Again, just finding the arc length of a parabola required integration by parts, required trig substitution, required the integral of secant cubed, required the integral of secant. Might be the most tedious problem in the course.